Okay, good morning, class. So let's begin today's lecture. I hope everybody is doing well for this quiz. So in the last lecture, we introduced the concept about what kind of crystals, what kind of lattice plane you might have in the crystal. So in today's lecture, we're going to talk about how does lattice crystal give rise to scattering signal, and how do we understand those type of scattering? How do we understand scattering from a simple single crystals to more complex form? We will also discuss about some ideas people develop to help you understand scattering, especially the concept of Edwards sphere and inverse space. Okay? So let's come back to here. In last lecture, we introduced a very simple concept to comprehend what is Bragg's law in terms of how these different lattices and how do we interpret those lattice spacings. So today's lecture, let's continue to talk about. First is where all these different indices correlate to in the scattering. So we talked about different nomenclature. Let's do it one more time. Example of 2D Miller indices and lattice spacing in this case. So in here, we showed a couple examples. What are scattering originate from, and how do we read them? So in this example, we showed a bunch of two-dimensional lattice plane. This represents, since it's two-dimensional, you only have two numbers, right? You have 1, 0, 2, 1, 1, 0, 1, 3, and 4, 1 minus. So those type of plane are directly visualized here. So if you have this type of structure, A is representing in this direction B. So 1, 1 means we're going to look at any structure that parallel to number 1A, number 1B. So this direction, okay? So if you have scattering, it arises from the parallel interference between these two lattice domains. So if you do, if you apply Bragg's law, 2D sine theta, this is the D refers to. And that's called a D11. D reference to the 1, 1 domain. So you can also have 1, 0 plane. It intercepted with A plane at the number 1. B, 0 means infinity. It does not intercept with B plane, so it will be parallel into B, but intercept at this distance, which is shown here. Okay, that's a representative for 1, 0. 2, 1 is shown here. And how do we interpret 2, 1? 2 is actually right here. 2 means second order peak. So it will be half in A, but it will be 1 means intercepted with 1B. Okay, so this translates to, if you draw a triangle, this means intercepted with 2, A divided by 2, and 1B. We also have interception with 4 minus 1, 1/4 of what the A lattice is, minus 1, which is here. You draw a line. That's going to be representing the 4, 1 plane. As you can see, the distance changes if we have different orientation coming from different scattering geometry. So this will be narrower than the other, and we will talk about what's the relationship. Last example is 1, 3, but hopefully everybody gets how do we label the peaks next time when you read scattering. To better understand it, we actually think about a reciprocal space. Reciprocal space is just the inverse of the real space. Again, those are the same lattice plane we draw. 1, 0, 1 plane. This is only one unit cell. So okay, this is A from top to bottom, B, And O1 is referring to this direction, right? O2, O3, you have O4. Again, 1O is other direction. 2O is half of that. Then you have other complex number. It's a little strange because when you talk about this 1O, 2O plane, it's actually easier to understand in the inverse space. Inverse means 1 divided by the value we had there. Why this is useful? So now if you look at the inverse space, if we use 1 divided by the distance, real distance, 1O, going to be shorter than O2. O1 will be shorter than O2 in here, right? O1 is half of it, because in real space, it's double the length. In the inverse space, it will be twice longer. So now the beauty of inverse space is now you can easily count like a typical coordinate you learn in your math class. O1 just means there's 0 coordinate in A and 0 in A, unit number in B. 1, 1 is this particular direction. Okay? It's quite simple, isn't it? Why people do this? Why people do a reciprocal space? There is a particular reason. We're just going to go into that. But for now, please understand, in real space, what we label is called the Miller indices. In the inverse space, we don't call it Miller indices, but it's also a type of labeling. Take a moment to digest this. Any question?
So this can be expanded into the K or the Z space, right?
Yeah, absolutely. This is a 2D dimensional, easy to show on the slides. So your dimension will be given by this vector. Very simple. D is star means complex or inverse. So in the inverse space, HLK will be given by how many numbers of unit vectors you have. H means 1 unit vector. K means unit vector for B direction. L means unit vector in the C complex direction. Okay, so then when we talk about we have scattering comes from 4, 1. That is exactly going to be count x equals to 4, a equals to 4, b equals to -1. And the length of this will given by the value of h squared plus k squared plus l squared and equals to d squared. Okay, that's just in this case, it's a triangle, okay? So if you have 4, 1, this will be equals to root square of 4 squared plus 1 squared, so root square 17 gives you this particular length. In this way, you can understand how does each Miller indices peak should translate into your real space periodicity in Q. Any questions so far? If not, then let's give you a few more examples. On the left, we show real space. On the right, we show again example reciprocal space. If we have orthogonal dimension or one dimension, it's very easy. We don't transform any lattice, but we only transform the length. So in the top, your periodicity A will be equal to reciprocal space will be 2 pi divided by A. Okay? And in here, if you have a lattice looks like square, your A1, A2 will be becoming complex, A1, A2. In the hexagonal, there is a little bit complex. the complexity comes from because this angle is no longer 90. When we do the reciprocal space versus real space, we need to consider a complex number relevant to the angle, this particular value phi. Okay, if it's 60 degree, the value is given here. How does it link to the reciprocal space with real space? So let's take a look at the application. This actually need to consider something called Ewald sphere. Someone named Edward, or short for Ewald, developed this concept to help you represent all the possible scattering. So how do we read this particular Ewald sphere? First, it's a spherical structure. So you can just imagine it's a sphere with a radius of 2 pi divided by basically your q vector, 2 pi sine theta divided by lambda. Or a lot of time, people would put for short for 1 divided by lambda in the diffraction community. So you can think about it as the incident wave number. When we talk about elastic scattering, we know the incident wave and scatter wave is the same. So this means you only bend the angle of your scatter beam, right? So this particular Ewald sphere is basically tell you all the possible scattering direction could happen when you have a transfer of vector q. If you go straight, there's no transfer in scattering vector. If you scatter in this direction, you need to map this q value. Okay? And we said about when you do scattering, basically you can consider a scatter vector will be equals to some real space dimension. So a simple way to apply this Ewald sphere is to apply it to the inverse space, not real space, okay? It has to be inverse space. So for example, this is the inverse space lattice we draw. This is the Ewald sphere. If we know what the k value, we know the radius, we just draw a radius like this. Now, we can place this particular sphere into your crystal. Okay, there's a few things going to happen. Depends on where your top circle, bottom lattice are oriented to each other. There is a few possibility that your sphere will sit right onto a particular sample or the sample point. Okay? We need to keep the incident, of course, aligned with one sample. So in this case, you can see there's this circle matches this star, and potentially here, but nothing here, and probably here, right? So what the meaning of when we apply the Ewald sphere to an inverse space? If they overlap, that means you could have a scattering happening at that direction, okay? Because this particular sample vector matches this Ewald sphere transfer or momentum vector when you have a scattering being in that direction. There is a nice cartoon I pulled online. So this represents the Ewald sphere is not moving. Okay, it's fixed. Now what we are rotating is a lattice in the inverse space. Okay, you can see something is rotating, all these dots, right? So that means X-ray is coming in at the given direction. You're having your single crystal. Okay, this is a single crystal moving around. Whenever your single crystal in the inverse reciprocal space intersect with your sphere in the outer shell, it has to be in this sphere, not inside it. Okay, it has to be, I should say, on the surface of it, right? Then you satisfy scattering conditions, you would be able to scatter in that particular direction. So for single crystal, when you rotate crystal, you will see not only just a peak rotated, with sometimes they disappear and emergence again. That's because sometimes rotate in and sometimes out of this your sphere and satisfy or not satisfy this scattering geometry. Okay, so any questions so far for this part? That's a very, very direct way to help you understand how your lattices, how your polymer crystal interact. So in the real case, if you just throw a sample, you're not rotating it, that's fine. There's always some chances of intersect. So in this way, the X-ray will diffract in this particular direction, as I show these yellow arrow, and your detector will be able to measure diffraction spots coming from that particular angle. There's some special cases that we call the extinction conditions. Those extinction conditions just means when a certain scattering geometry met, some of the higher order peak will disappear just because you have interference within this scattering lattice could cancel out each other. Next one, we're going to talk about a few useful things within this particular scattering. So how do we use then scattering to do useful things? There's a couple things we do. We're going to talk about a couple of them, but a couple concepts I want to cover here. The first one is scattering. Sometimes you need to consider this is called the Debye-Waller factor. So this is very simple to understand. This is a thermal-induced widening of diffraction peak. In the example, we show that if you have a perfect lattice, then you wouldn't not necessarily have any changes in the position, right? So this is a lattice, this is an atom. So when you have at rest, you basically your scattering can be given by scatter vector and where the atom positions is in it. So looks like this one. But when as we know that any material that is not at rest, it will have a certain vibration. Vibration means even everybody sitting on your chair, you're not perfectly stationary. Right, you move around, you stretch your arm. So this creates slightly motion off your center position, which you're supposed to be sit in this lattice spacing. Okay, this shows example here, and this sometimes there's two parts. This is very similar to translational disorder in a lattice, but this is also. In this case, this also comes from the vibration of your material. I don't need to go much to in the math. Basically says we need to consider R is where the position of your atom is a function of time. This is equilibrium position where it's defined by Rn. And there is tiny displacement term we show here as U, which is dependent on time. So this U just says there is a certain small displacement. R means there's defined average distance between different moments. Don't need to go too much into the math. So basically it says this, now your form factor need to consider this EXP versus U, which is the scattering term coming from your shifting from the center. We can expand it using a Taylor expansion. We can get these terms. For the first term is basically, this will cancel out each other because average G dot U, because U is not sometimes point left, sometimes point right, so it will cancel out over time. But G dot U square will not cancel out. And if we apply the mass to it, it will give it as equation shows here. So we can simply write scattering intensity would be equals to, this is static term, where you don't have anything move around, I0 for a perfect crystal. But when you have polymer, any crystal at elevated temperature, it's not stationary, then you need to consider this exponential term, which depends on motion of your molecular in the crystal. And the higher this motion, your peak will show a broadening effect, okay? So that's where the Biwalla factor is basically a thermal vibration within your lattice can cause your lattice, your scattering to be broadened. There's also another factor comes into play, can triggers your peaks to be broadened, as we mentioned. The translational disorder, this is inherent to your crystal. So if you have the crystal is not perfect, you would also show up. So you have to differentiate these two. The other part that is very useful for scattering is we know this is perfect to measure. Even it's broadened, let me add one more point. Even it's broadens, the average distance r can be easily measured because broadening doesn't change average spacing between r. So if you do diffraction, you find a peak. The location of the peak is always going to be correlate to the average distance of your lattice spacing. In this case, this is one of the lattice spacing direction. There's other things we can talk about is how many of these are located in one plane. If everybody recall, we discussed about Fourier transform. If you have an infinite narrow sample, then your peak will be infinite broad. If your sample, the crystal, is infinitely long, the Fourier transform will give you infinite sharp peak. However, in real case, we never have either of the case. Our crystal will always have a certain dimension. So let's say some crystal are a few microns, some are a few millimeters. So the degree of crystal perfection and the size of it come into play as well. That's where, let me first finish this one. That's where the full width half max comes into play. This is very relevant to the last topic we talked about, right? So full width half max defined as what is the width of your scattering peak with respect to the half of the maximum intensity. So you can imagine this will give the width of your peak. And this is inversely correlated to your size of crystal. So if your crystal is very tiny, you would get a very broad peak. If your crystal is large and perfect, let's say single crystal, you would have a very, very sharp peak. Okay, just because the finite size effect. So the width of your peak can also be used to understand the coherence length is typically used by 2 pi divided by q. Sometimes people also give a constant in front of it, k, which is equal to 0.9. So this gives you some idea what is coherence length. Some people just call it crystal light size, but that's not the case because crystal lights is more complex. If there's defect in it, your coherent length will drop. So I would like to argue we should always call it coherent length. But conceptually, you can think this is relevant to your crystal light size. The smaller the width, the more nicer your crystal is. Okay? And you can use this value to say my coherent length, or if the defect level is similar within the same material, then I can say my crystal is a few microns or a few nanometer. Any question?
So regarding the term, so the smaller the crystal, we say that it has a shorter coherence length?
So let me explain. Yes, you can say there. Smaller crystal always going to result in smaller coherence length. The maximum, if your crystal is perfect, all the dots are aligned perfectly, then your coherence length is going to be as big as your crystal. But let's say in the middle of your crystal, you have some defects, your crystal is bending in a certain direction. Although your crystal is the same, let's say 1 micron, but only half of it will contribute to this forward half maximum. So we call it coherence. In this case, coherent length will drop from, let's say, 1 micron to 500 nanometer. It will scatter or diffract as the same as smaller crystallized but perfect. So it's hard to directly translate to the crystallized size. So more technical, corrected term is just call it coherent length. Okay? Okay, so let's talk about this slide. This is more relevant to the quality and the distribution of your crystal orientation. We talked about crystallized size. How does crystal orientation impact is we call the scattering mosaic spreading. So if you have a crystal, imagine these represents one crystal. If it's a single crystal, everything is one large crystal, then your diffraction should behave fairly like the top one. Because one certain lattice orientation will give a certain scattering orientation, be reflected here. So if you have a certain wiggling in the orientation, this orientation will give a scattering at this particular scattering peak. And the more wiggle you have, for example, this one is a little bit bent to the left, it will result in scattering dots or scattering peak showed up a little bit left. So you would have spreading of your peak. So let's use example. This is one single crystal. This is a polycrystalline. So within the crystal, let's say you have 3-4 different large crystal orientation. Then you can imagine now each crystal will diffract like this, but they're oriented in slightly different orientation. Take a picture of this, same one, rotate the lattice by a few degrees, overlapping back to what the original is, you would reach this pattern, okay? So this is a very common polycrystalline material with a few different orientation. Of course, this distance will not change because that defines your crystal lattice. But where these bright spots show up now shows you what's the relative orientation within it. So this maybe have 1080 different orientation. So think about in this classroom right now, everybody stand up, right, straight, or sit down, like this orientation. But if some of you are lying on the floor, some of them orient 45 degrees, you would come into that. Now think about it's even bigger, not just a classroom. We have the whole university, 20,000 students doing all kind of random things. Your dots gonna connect, since it's random, so what kind of distribution is possible? This is gonna connect into a dot. Of course, this is a different sample, okay? But you got the point where this ring or arcs or dots are coming from. Orientation of your crystal. If it's random orientation, you would form a ring. We call it anisotropic. Any question for this part? Yeah.
So you use this to describe basically the phase of where it's at of your crystal base with the smectic or somatic versus the pneumatic and isotropic disorder, correct?
So short answer is no. This does not direct translate to any liquid crystal. So in the liquid crystalline phase, it's different. In this, we strictly are discussing about crystalline structure. So this will be crystallites of polyethylene, crystallites of salts, sodium chloride salts, or crystalline structure of gold nanoparticle. For example, if we convert, as the distance to the center is the same, as we talked about in the last few lectures, we can convert this from intensity. We call two-dimensional image. If we do cross-section along this line, we basically get intensity versus scattering vector Q plot. It's the center is smaller Q. This is higher Q. You would show this. Of course, in this image, we didn't show very clearly a lot of high Q, but those two peaks I show translate to here, and there's a couple more here. Okay, so this will allow you to analyze how wide the peak with the lattice packing. So for example, you know the peak position, and you can fit the peak position and look at the peak ratio. This tells you a lot about how the crystal is packed. And based on those information, where the peaks are, you can get lattice spacing, lattice constant for this particular material ABC value. You can look at the width to understand your crystal quality or coherent length. And it's sitting on a very broad peak, right? So if you only have this crystal peak, and if it's a perfect crystal, it should show a Gaussian peak. So which means it will be fairly sharp, look like this. And what about these large tails? Those are we call amorphous halo. If you're coming from amorphous structure, we know that you would have, if you have amorphous structures, very much like liquids. Liquids still have a little bit short range order. So you would have this very broad peak translate to amorphous scattering from your material. Okay? And if you actually heat the sample, this particular one, in real time, you can do heating. Your crystalline peak will disappear. And at the end of the day, if everything is melted, you would have a large amorphous peak. I think that will be it. Oh, there's one last thing I think I missed. This is just come back to show you what the Debye-Waller effect that comes into play. So this is example, I think they showed a couple different cases. You can look at the Debye-Waller effect at the different conditions will allow in diminishing or weakening some of the peak. But interestingly here, you need to convolute the crystallite size with a couple factors here. First, this assumes that your instrument is not limited by your crystal's intensity, okay, for this full width half max. That means your instrument can resolve as high as this kind of width. But instrument has a certain limitation. So if we have, let's say, a crystal is perfect, you should have infinity sharp peak. Right, Yunfei? Good. So if you have it's really sharp, then you could have a problem because your X-ray comes in is polydispersed. There's also spreading at the STD a little bit. So the instrument has a certain limitation that it can only measures peak width to a certain value. So for example, if my instrument can only measure peak to this wide, then the value what you measure is limited by instrument. So you should always consult with a binary scientist to understand what the instrument resolution. And instrument resolution is not particularly limiting your observing the crystallite size or full width half max. What else? I think that's pretty much it. All you need to know so far for order structure for crystallites, etc. So any question for this part? If not, so we kind of covered most of the basics of scattering and ordering. So I want to spend a couple minutes just remind everybody how we get to this stage, because those are all the fundamentals. I think then if everybody understands those far and following has no problem, we should be all set for the theory part of our scattering example. Next phase, we're going to go talk about a few examples of scattering. So in October, we're going to discuss a couple typical applications. I'm going to send everybody some papers, and we can take a look and discuss in those real examples what techniques people used, what information they extract, and why X-ray is useful in those cases. Okay? But all the knowledge we learn here is fundamental and essential for you to read those works. So think about what we did again. I think key things or key take home away is you need to understand what do you need X-ray for. We talked about there's two key things you can do. You can either look at the form factor, you can look at structure factor of your material. So if you only just want to look at form factor, you should think about looking at very dilute sample, looking at their shape, looking at their size, and make sure your measure size scale matches. And typically form factor is measured at small angle region. In the wide angle region, because the X-ray Q is so high, you're looking at tiny features. It typically starts to matches lattice spacing within your material, and that results in very hard to resolve because you have interference from crystallized structure. Okay? So we talked about how scattering comes from electrons to more complex form, to atoms, to moleculars, and then you have molecular packed with each other to form lattices. Okay? So it's quite nice and quite important. Everybody go back to revisit what are those structure factor, form factor is. We talked about also more recently talked about special case is looking at the structure factor in the crystal, looking at lattice packing, looking at what kind of crystallized structure you have and how you can extract lattice packing using Bragg's law. Shear equations is something we use to extrapolate this crystal size, etc. I think that will be all we need to know so far. Any question? Okay. If not, please.
About the proposal, are we still shooting for October 1?
Yeah. I actually was about to mention that. So October 1 is Friday. So I will come here to answer any questions if you have. So please go back to read one last time from chapter 1 to chapter 4. We already covered most of it. Okay. There's a couple of small things we didn't cover, but I'm happy to chat with you if you have questions. I'll do an office hour Tuesday, and I'll get the Thursday off. So we don't teach next Thursday. So everybody, I'll give you some extra time to write about the proposal. But I expect to receive it by Friday evening. Is that sounds good? Okay. So
we're submitting it on actual Canvas, right? Or
either way. Yeah, I don't have a preference. Well, pick the one your favorite. Then in 2 weeks, in Tuesday, we're gonna now start talking about scientific cases. So I'm gonna give you a couple examples how this being applied to looking at crystal structures, looking at block polymer, looking at polymer composites. I'll pull literatures and give an example, then we can discuss about that. Okay? Then I also read your proposals and try to group people with interest in the technique. So in November, we will have more hands-on to run your samples. We may not have time to run every single sample, but at least within a group, within similar scope, we will run a couple. We will invite some special lectures. Actually, I came up with this good idea. There's a few researchers in the field. I talked to a very well-known professor in the Case Western, Michael Hoare. He works on nanoparticle composites with polymer, so he kindly agreed to give a special lecture to everybody about his research. And we're trading horses, so I'm going to give a lecture for his scattering class as well down the road. And I'm trying to have another beamline scientist coming from, haven't decided the final time and date yet, but ask this particular person to talk about their beamline and how to write proposals if anyone is interested. So there's going to be another special lecture targeted for introduce everybody about National Labs resources outside USN. Then I think that's a plan. Okay? If there's no more question, then let's end today's lecture.